So how many of you actually did watch the video yesterday? Even if you just skimmed through it a little bit. Okay, a couple of you. So those of you who watched the video yesterday, great. You've already seen what I'm going to teach today. It's just a different name for something I did yesterday. So, impulse is simply the change in momentum. So instead of putting down the whole thing of change in momentum, we can just call it impulse. And this is shown up there on the board. Remember delta? Delta is change in, and then we've got the Greek letter rho. It looks like a P. It's not a P, it's a rho. Most students still write it as P, and that's fine. So impulse is just another name for change in momentum, which I talked about yesterday. So where this, we're going to define a second part of change in momentum. So looking at Newton's second law. So Newton's second law says force net equals mass times acceleration. Acceleration is change in velocity over time. So therefore, based on this fact, we've got change in momentum is two things. It's mass times change in velocity, or it's F net times time. Both of these work. So yesterday in the notes I said that momentum can also be newtons times seconds. Here's where that comes from. Force is newtons, time is seconds. So this is what impulse is. Change in momentum is your impulse. So depending on what you're given in the question, you're either going to do change in velocity times the mass or F net times time. Anyone still writing that out? You don't necessarily need to know the derivation. That's just where it comes from. Just waiting on you. No pressure. Got it? Perfect. So fun fact. So how long does it take a fully loaded supertanker? So a supertanker is just a big semi-truck that carries whatever tank of liquid you got. So if it travels at a normal speed of 30 kilometers per hour, how long do you think it takes to come to a complete stop? Any guesses? Any of you planning to be a truck driver at some point in your life? 2 seconds? Okay, I've got one guess. 20 seconds, I got another guess. Anyone else? 20 seconds, okay. Anyone think 2 minutes? Anyone think 20 minutes? Adam just for the sake of saying it's 20 minutes. It's actually, it depends on the mass, it depends on a few things, but it normally takes between 20 seconds and 2 minutes. It usually takes about 5 kilometers for a truck, like one of those huge trucks, to come to a complete stop. So they have a lot of momentum, they're really heavy, so it takes a long time for them to come to a stop. Just a fun fact. Okay, so we've got Luigi. He doesn't like to take orders anymore, so he swings a hammer at Mario's mustache, and the mustache brings it to a stop in 0.25 seconds. What is the net force exerted on Mario's mustache? So we've got 3 parts of an equation. Change in momentum, mass times change in velocity, F net times time. We only need 2 of those. We're talking about a change in velocity, and we're talking about time. So we're going to use just the last 2 parts. So m delta v equals F net times time. I've got mass, right? We got the hammer. We've got a change in velocity. It's going 16 meters per second, and then it comes to a stop. F net's what we're looking for, and we have time. So mass is 9. Change in velocity is final velocity, which is 0, minus the initial velocity, which is 16 meters per second. F net, and time is 0.25. So solve for F net. So doing this, what do we get? 9 times negative 16 divided by 0.25. So negative 576. If you saw this on the worksheet with the answer key, they'd probably round it to negative 580. Just because of sig figs. So why is this negative? Why is my F net negative in this case? It's bringing it to a stop, so F net must be in the opposite direction. So that's what the negative here tells you. It just means it's in the opposite direction. So Luigi is applying a force this way. So Mario's mustache must be applying a force in the opposite direction. That's why this one's negative. Let's try this one. So we've got a football player who's kicking a ball, and the goalie's going to bring it to a stop. We want to know how long does it take to stop. So again, even though we're using the impulse equation, it's not actually asking for the impulse. So you're going to need to be able to recognize that on a test. So let's try this. We got m, change in velocity, F net times time. What is it asking for? It's asking for time. So we got the mass, 0.45. Change in velocity is bringing it to a stop. So the final velocity is 0. The initial velocity is 25. Oops, that's a weird 5. 25. Notice I'm given a direction. So that's important to note. This is equal to, we're told the force, 215, times the time. So solve for time. Doing the exact same thing, 0.45 times negative 25 divided by 215. We get negative 0.052 seconds. So time is a scalar, so we don't need to put any direction with that. But there should be a lot of you that see something wrong with this. Can I have negative time? No, not unless you're watching the movie Tenet. So we don't have negative time. So what went wrong in our equation? 0 minus 25, okay. So is my final velocity 0? Yes. Is my 25 in the right direction? Yeah, because it's east, so that needs to stay positive. 215 is in the opposite direction. So because the F net is in the opposite direction, this needs to be negative, which will make this positive. So this is what's going to trip up a few students on the test, because if you just take away the negative, you won't get the full marks. You need to be able to show me that you understand the F net is in the opposite direction. Yeah? So if the ball's going this way in the positive direction, the force that the goalie applies to stop it is in the opposite direction. So it's opposing the motion. So that's where this comes into play, is just looking at forces in the negative direction. So that's what you got to be careful of with this. Any questions on that? Give you a sec to write it out. So this is going to be the first unit where you're going to put in some negatives with forces. So you're going to need to think about that a little bit. But essentially it's this. If the force is slowing down the object, it's negative. You have a negative acceleration, it's slowing down. So now we're going to do the same thing, except we're going to deal with a different object. So now we're told, doesn't want to erase. Now we're told the goalie is stopping a bowling ball and it's moving at the same velocity. And we want to figure out how much force is required. Same velocity, same amount of time. So we're going to use the same equation. M delta V equals F net times time. So what changes in this question? So F net's going to change. What else changes? Mass. So my change in velocity is the same. My time is going to be the same. So my mass is now 6.5. My change in velocity is still negative 25. We're solving for F net. Can someone remind me what the time was? What's that? 0.054. 2. Thank you. And solve for F net. Sounds about right. Let me double check. Nice, an exact number. And this is negative. Does this number make sense? Why? Why is this one so much larger force compared to the force here? The mass is so much bigger. If you're trying to, if someone throws a soccer ball at you or throws a bowling ball at you, you're going to try and stop the soccer ball. You're going to move out of the way of the bowling ball. You don't want to try and stop that. Any questions with this one? Is this the last example? No, I've got a few more. Okay. So now for some thought experiments with this. So a student jumps off a desk. I don't advise it. When they land, they bend their knees on impact. So why does that prevent injury to your knees? So think about if you're jumping off of something. When you land, you will typically bend your knees at the bottom. So they don't break. Yeah, if you land with your legs straight, it's going to hurt a lot. But how can we relate that to what we're talking about now? So this has a lot to do with impulse. So let's say we're thinking about if you do bend your knees compared to if you don't. So if I bend my knees when I land, will my mass differ? No. If I land and stand straight, or if I land and bend my knees, this is not going to change. So this is constant. That's not going to change. Constant. Does my change in velocity change? I'm going to land with the same initial velocity. I'm going to come to a stop. So this is constant. How about the time? The time it takes me to come to a stop. If I land straight-legged, or if I bend my knees, will bending my knees change the time it takes to come to a stop? It'll take longer, right? If you bend your knees, you'll absorb some of the impact, so the time it takes to stop increases. So if the the left-hand side of my equation is a constant, and on the right I increase a value, what must my F net do to maintain a constant value on this side?
Decrease.
This one has to decrease. So by increasing the time of contact, I'm decreasing the force. Does that make sense? This is why you have airbags in a car. The longer it takes you to slow down, the less net force you experience. Let's try this with a different example. So we've got a few athletes in here, I'm sure. So this applies to any sport: baseball, tennis, golf, football, squash, I don't know what else, water polo. Any of these, your coach is going to tell you to follow through. Okay, no one tells their players, okay, if you're going to kick a ball, kick until your foot touches the ball and then stop your leg. Right? They tell you to follow through. So you swing with your leg and you follow through the ball. Or when you're swinging at a tennis ball, you don't just hit the ball and stop your hand, you swing all the way through it. It's the exact same principle, except we're going to change something a little bit. So we look at the exact same equation here. So m delta v equals F net times time. The mass is going to be constant. Okay, the ball's not going to change. The amount of force that you're applying is going to be the same. But if you follow through, you're going to be in contact with the ball longer. So think about it. If you're hitting something, if you just hit and stop, you're not in contact for as long as if you hit and follow through with it. So in this case, your time increases. And if one side of the equation increases, this side must also increase, because we're dealing with the opposite side of the equation. So by following through, you're going to create a bigger change in velocity. So weaker players will be able to hit farther the longer they're in contact with the ball. So you can use this equation to compare a lot of different things, and why it's better to have follow through with this. It's the same thing. Does anyone here do like boxing or martial arts or anything like that? They tell you to roll with the punches. Have you heard that phrase before? Or is this more an English term? So roll with the punches. So if someone punches you, you don't try and hold still. You let them punch you, and you let your face move with the punch. It's the same principle. My time is going to increase, so the net force will decrease. So this is a very common occurrence with that. I talked about that, and that's it. I'm not going to go through the airbag one. We already talked about that. So that's impulse. Those are the two equations with that. You've got a worksheet that you can finish off for this. The big section for this unit is going to be conservation of momentum, which I'll do next week with you guys.